原来你讲话他们是听得到的。
我有听我讲话吗？
我刚刚这边开另一个 meeting 嘛，然后突然间你在那边讲话的时候，这边有声音了。
可我刚刚没有讲话。
有啊，你看嗨，
啊，
你看好，嗨，然后突然间他就 record 到了。
对啊，
嗯，
我车就没有录进去啊。
哇，做乜㗎？
you are pressing on your cable again. There we go.
對，我要回來
Okay,
了
I。think they can hear you.
Just share this.
Focus. You want to move it? I think that's all right.
Okay, so you can see, right?
Yeah, they can see it.
Okay.
Yeah.
okay. This is
So you simply do transient, you just zoom into where you put your, previously you created DC voltage for your common mode voltage, right? Yeah, you zoom in there. Yeah, instead of creating a DC voltage now, you're going to create a AC voltage. So let me zoom in first. I think where
I think
where is
we
your
use,
DC or VE plus here, right?
I think we use VPWL, right? Because when I do transient the other,
Hold on, I think this one the 4.5 is you manually type it every time you did.
Yeah.
Do you create equation VDD over 2 or you every time you run then you
On my current source one that I did, I put it as VDD, then I run it using the equation for the current source only lah. This one I haven't.
okay. Maybe later on to test whether your power supply. I think to test for whether this is important later on. For example, your VDC for your VDD, you put as VDD, right?
Yeah.
Then this one you should be in VDD over 2.
yes.
Yeah, and then you try to do the same for this one as well.
Yeah.
Then you try to switch for supply voltage of 5 to 15. Then you see whether when you switch it, or you can no need to switch as well. You can just pick a few points like 5, 10, 15. You see whether all the operating points of your MOSFET are still in saturation or not. If let's say the two extreme points they are in saturation, I think you can more or less say the middle ones they are all good already.
Mhm.
Yeah.
Okay.
So I think this one later on. So this one you need to remove the DC voltage now. You replace with a AC voltage. So I think you can get from the same library.
Analog isn't analog.
Yeah, correct. Let's
I
see.
think it's this one, right? VPWL. Pulse width.
I don't think so. But V pulse is square wave, no. I think there is something let's go up a bit.
I think I tried VPWL before. It's you just put a time and the voltage, and you can control if you want it to be linear or square wave.
Oh, okay.
Yeah.
Okay, you can try this. Yeah, some of these features they are.
Yeah, it looks like something like this. You just control how you want it to be.
Can you make it a sine wave? Is it possible?
Sine wave? No, I don't think so.
Hey, I think you go to Vsauce. I think there is
Vsauce,
for Vsauce. Okay. Because I don't recall clicking on this. There should be something like a
This
Vsauce. Yeah, you try to see first.
Yeah, there's.
Yeah, okay, yeah, this one. Okay, now you click on it, and then edit the properties. You change the source type to AC. Let's see what happens first.
For sine.
Sine.
Sine. Okay. Now you don't need to do any offset. So now your DC voltage is your average, which is the common mode. Yeah, so your DC voltage you put VDD over 2. Yeah, type the same. I think you cannot.
Small letter.
Yeah, small letter. I think. Yeah.
All right.
Okay. Now you have. I think you have the amplitude. Yeah. Voltage amplitude.
9 or VDD.
I think for amplitude, let me think first. If you want to do transient analysis, you can put. Okay, I will say better don't switch first. Let me think first. There are many ways we can do it. To do transient, you also can, for example, to do transient, last time we have 2 methods. Either you set the amplitude to a fixed value, then you see whether when it oscillates, you can see the oscillation of the input waveform, and then whether the output waveform is amplified and also not changed or not. if it's click off lah, if let's say output is click off, become flat line, it means that you have exceeded the voltage swing, the cap already. Yeah, so there's one way of doing that, or you can do it in a way where you can simply plot the peak to peak voltage of the output against peak to peak of the input voltage. So you will see that most likely is as the peak to peak input increases, most likely the output peak to peak will increase as well, right? And then you reach a point where no matter how much more your peak to peak input increase, your peak to peak output will simply remain constant. That's where it gets kicked off lah. So you know the operating region. So in this case, most likely you see like you begin with flat, more or less a flat, then slowly curve upwards, become a linear, then it will slowly become flat again. So you want to operate in the linear region.
Yeah.
Linear relationship between output and input. So if you can determine that the x-axis range is from 5 to 50 volt, yeah, that is you are really you're succeeding already. Yeah. So one thing we can do perhaps let me see. Okay, let's try a very simple one first. You can set your voltage amplitude. Let's see. Did they mention anything about the spec? What is your input voltage amplitude? No, right?
I don't think so.
Do I get the specs just to make sure? Because I don't think, where is it?
In
I
your
think we have it in the group.
I think there is some specs, like for example, they will tell you their audio signal, what is the maximum peak to peak that you can have for your audio. Yeah, that also affects that also affects how well your system perform. I can go to the
I mean, if you scroll all the way up to the media, they have the
Just get it from my phone, and I send it. Try to send it to me, so
I see the picture one that Kasiang sent.
try to find it.
yeah, this one, yes, correct.
So just forward it again. Okay.
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 So they also give us an input offset here. Should we also include it? Or?
Input offset.
Yeah.
Yeah, maximum is 10 milli. Yeah, you can do it later on. I would say better to keep all this constant first, means that you put offset to be 0 first. You test for some of the parameters, then step by step. If you put in too much at the same time, I don't think. Yeah, that's the industrial practice. Usually you test for just one parameter first. Okay, let's see. Large signal open loop gain. Okay. Yeah, so right now, yeah, we're doing open loop gain. They want maximum to be 100 dB. Yeah, they didn't mention how much does the input voltage swing. Yeah, I don't think there's a requirement for that. See, I think you can put how much will be a reasonable swing. Let me think first. Some no other things, right? Yeah, I think there's no requirement for that. Maybe you can just put, let's say you can set amplitude to be, let's say 1 volt first. Yeah, maybe here you set voltage amplitude. You put to 1 first. Okay, then there's no delay time. Yeah, I don't think you need any delay time for that. Then let me think first. Okay, wait. Then what happens to P minus? Because if you do amplifier in audio, you usually will do negative feedback. But then right now you're doing open loop. So open loop, let me think. If you do open loop,
Says output source. We supply 16 volt.
volt means at 16 volt you get 50 milliamp. Yeah.
Oh,
But then you're not necessarily getting that, right? So it doesn't matter.
oh, right.
Okay. Okay, I think in this case, in fact, okay, let me revert a bit. Because since for now, they just want you to make sure that the gain is within a certain limit. So we're actually not interested in how it behaves over time right now. I don't think you need sine wave at the moment. So what you can do is here, for example, your V in. So right now, let me revert a bit. I think this one you can later on, let me think of what kind of scenario you need this. But for now, let me see first. You even need this because you are not doing negative feedback. If no negative feedback, in negative feedback, what we do in audio is we supply sine wave to V in plus, V in minus with feedback. So in this case, if you are doing open loop, yeah, actually you don't need this first. This one you need first. You replace back the VDC. Yeah.
It's very lucky.
Okay, so right now what you do is you can put, let's say, V in. Okay, right now maybe what I will do since I don't want to confuse you, you can simply hardcode a certain value for your VDD. For example, let's say right now you choose VDD to be, let's say, 10. Okay, so maybe you treat 5 as an average. Not 5, sorry. Yeah, 5 as average for your V in, right? So okay, why not you do like this? For example, V in plus, you put a 6 volt. Then V in minus, you put a 4 volt. There's a difference in voltage.
Yeah,
Then you
yeah.
see how much that they amplify.
So this one's 6 and this one's 5.
Yeah, this one is 4.
Four.
Yeah, something like this.
4. And this one is
Put 6 and 4.
6 and 3.
Yeah, V in plus.
6.
Actually, there's one thing that I need to inform you about. Okay, so you zoom out a bit, you see your circuit. Yeah, this is one thing that actually, if you look closely at your lecture note, you notice that you put the polarity of your V in actually in the wrong place. Should be the other way around. Okay, let me tell you first. Because in op amp, the output directly on top of your MOSFET is inverted, right? If you have V in plus, this one is V out minus. If you have V in minus, this is V out plus, right?
Yeah.
And then you notice that you have second stage. Second stage amplification means that this also invert one more time. So if you put V in minus here, invert become V in V out plus, invert again become V out minus.
Yeah.
By right, this should be your V in plus. Plus, minus, plus. Yeah, so it should be the other way around. If you look at the lecture note of your day 2 or day 3, they actually mentioned that if you implement 2 stage, you invert twice, double negative. Yeah, so here you should connect to V in plus. Yeah, and then this one should be V in minus. Yeah, and then this one V in minus. That should be the other way around.
It's very.
Yeah, no worries, take your time. Wait, you're still here.
It's. It's not. There you go. Okay.
This one V in minus. I think you select more. Just cancel.
Should I use the mouse?
Yeah. Oh, I think you cannot unplug it. Yeah, they usually use a lock to.
Can just use yours.
They usually use padlock to lock it.
This one is V minus.
Yeah, correct.
This one.
Yeah, so
Okay.
correct. Yeah, now.
I change also here, right? This one should be V minus. Or it doesn't matter. actually.
it doesn't matter.
Doesn't matter. No, doesn't matter already.
Just put one here. Because it was both.
Yeah, right.
Yeah.
Okay, let me see first. Here, instead of doing like that, why not? Okay, because you are testing the differential, so why not you just put, for example, we just ignore the common mode gain. Right now, we are just interested in the difference in voltage. So 6 minus 4 is actually 2, right? Instead of doing like that, why not you just connect VDC between V plus and V minus. Because if you put a DC voltage between V in plus and V minus, there's a difference in voltage, right?
Oh,
Yeah.
Yeah, so it will just act like an open loop gain lah.
Oh.
Yeah, so what you need to do here is you remove this VSS line. And remove, and then you remove this whole thing. Yeah, you put V in minus. Yeah. You can name the net list as Y net V in minus. Yeah. Yep. Yeah, then you can simply, what you can do lah, you simply sweep VDC from 0 all the way up to any value you want lah. You can even sweep from negative lah, but then since we are doing single-ended lah,
Yeah.
there's no
Yeah.
point doing a negative lah. So
we call
actually,
it a loop array.
negative does it? I think maybe it's both lah, because let's say if you do negative feedback, yeah, if your output is actually higher than your V in positive lah, then you can actually correct that lah. So maybe what you can do lah, maybe let's say you switch from -5 to 5. Yeah, I doubt the audio will actually switch that much lah, but you can just switch like that lah.
Oh.
So here you can put a VD, VDIF lah, or VDIF.
But this is while keeping our VDD at 10 volts.
Yes, correct. Yeah, you can do a double sweep, means nested sweep. Yeah, but then let's do one scenario first lah. Yeah.
So
Can
we
open
call
the-
it
Yeah, so you can open your simulation now.
It's the schematic. Okay.
here's this.
You're right. Okay, right now you have VDD. You can set it to 10 first, maybe.
This one.
No, here you set your parameters here.
Oh,
Yeah,
this one done here.
Yeah, you can add all the parameters first.
But you change VDD to the specific value already, right?
No, actually he labeled VDD. I think it's an unknown here.
This is VDIF though. That one you changed to
10
Oh, okay. Put
So-
VDD.
So you can't put VDD.
Yeah, correct.
Yeah.
Right. You should put VDD. I think you just name the value as VDD lah, so that when you run simulation, you can add it straight away on your
Oh, okay.
test bench. Yeah, maybe you can use test bench to import all the variables first.
Yeah.
How?
Variables, copy from design.
Okay.
Yeah, you only have 2 lah. Since you already hard code the rest of the weight lah,
Yep.
there's no need to.
So VDIF, we just give it what value first? 2?
VD we are going to sweep it.
Yeah,
So
so-
maybe
so-
we put at -5 first, then later on we will initiate a sweep here.
So setup analysis.
Yeah,
DC.
you put DC sweep.
VDIF.
Yeah, VD.
Fine.
From -5
Yes.
to
Stop at 5. Then the step size, yeah, you can just maintain at 0.5. I think it's good enough. Then okay. Yeah, then you need to input your output here. I don't think you're interested in all this anymore. So you untick them first. Yeah, I think V out here. Where did you put your initial V out? I think you can put V out 1 and V out 2. First
Sorry.
stage and second stage. Then you can actually see lah, which part of the V out has a problem, which parts gets fixed first. Then you actually understand that. So maybe this one you name as V out 1. Yeah, and then this one you try to see where you
this one I put it in. Sorry. I put it here. This.
okay. This one, right? So this should be your V out 2. Yeah, correct. You go back. You go back to your test bench.
Mm.
Yeah. Maybe we just link from here. You click on this expression, and then you can select the this one. Yeah, correct. And then you V out 1, you click here first. The first stage. Yeah, the first stage here. Correct. And then the second V out 2. Click on here.
Same here. In the second stage.
Yeah, I think you click the line means this is a current, is it? Or then
Oh, this is a voltage.
Voltage.
If you want to click on current, you have to
Okay,
choose
on
the
the-
term. Yeah.
the node there.
The not in the current.
Okay, the other way around.
Yeah.
Okay, click here. Yep.
Mm.
So right now you have 4 of these. Then we're going to sweep this. We're going to do a DC sweep for 4 of
Mm.
these values. So you can click on the waveform. Yeah,
Yeah,
for these 2.
yeah.
V out 1 and V out 2 here.
Okay. So everything. I don't-
Yeah, then you can run the simulation. I think that is true.
Oh, I didn't save. I think should save it.
Sometimes it doesn't. Check first.
Okay, I'll just let it run it again.
Yeah, you can actually see that this is the relationship log. So you can see that the walking range, maybe you can split these two. I think it's getting a bit, you can, what you can do is you can right click on this. You can right click on the whole box here, put ungroup. Yeah,
Or ungroup it.
yeah, ungroup it so that you can see the two graphs separately. Click on ungroup.
Okay.
Yeah. So here you have, wait, you have two out here.
Or you put pen instead of place with it.
I think I'll just
Okay,
reset. Yeah, reset,
yeah, reset
it, so
everything,
we
yeah.
don't get confused. Yeah. Just close all of this.
Yeah.
Then
Make sure you can save it. Your
In transient, you don't actually, I just recall, if you want to test for all the gain and stuff, you just need DC. Transient is only needed for your sleep rate. I think they mentioned about the sleep rate.
yeah,
How fast, how long does it delay? Yeah, I think that one you just need to
storage
see.
is transient, is it?
Yeah, transient. You just need to see how fast does the slot rises with respect to time. Yeah, I don't think transient is that important here Yeah, I just recall actually not that important.
Yeah. Just
Run first, yeah.
now it's only two.
Yeah, group first. Okay, you can see this is your ultimate, the really second stage output, and this is your first stage. So you can see that your op amp here, best if, so as I said the best working region for your op amp is where your output voltage increases linearly with input voltage, right? So the more your input voltage increase, your output voltage also increase by a certain proportion. Means that you have a constant gain throughout the region. And this is where your gain gets clipped off. Means that you can see that let's look at where the region way more positive first.
Yeah.
This is where your input, let's say maybe I give example, maybe let's say your gain is 2 times. So your output is actually V in times 2. So this slope is simply a constant gradient, right? This is where your gain is constant, and this is where no matter how much more your V in increase, your output is just capped at this limit. You can see that the limit is about, you can simply hover over here. You can use a cursor. I think you can use this. The first one, yeah. You can switch to horizontal actually. Is it right click
Disadvantage.
or hash? Wait, no. I think you right click first, you see. Oh, no. Okay, somewhat I forgot how you set. I think you can click on axis or what, tools or what.
Maybe I can do like this.
Yeah, can. I can go all the way to here to the here. Okay, you see, your output go all the way to the right. Your output is capped at 7.6 amp. So that's the maximum your output voltage can swing. This means that let's say you have a sine wave. If your output voltage tends to swing to a peak more than 7.6 amp, it will get clipped off. So you see your, later on you can try that. You can try giving, for example, later on if you want to see how it works in real time, you can replace back the AC signal that we just put in.
Okay.
You create a sine wave input. What I will do, let me see. But then let me see an open loop of, if I put in, okay, what you can do is like this. Okay, maybe for example, I will maybe make V in minus a 0 value then you simply swing a sine wave that is with a maybe, okay, what I can do is like this. You put V in minus to be VDD over 2. Then you put V in plus to be a sine wave that swings around VDD over 2. Yeah, then you can see that how, depending on the amplitude of your sine wave, you can see whether it gets clipped out or not. Later on, we do a simple experiment, don't worry. So you can see that your maximum value for your V out is 7.6 at, go to the way to the left. drag it all the way to your left. Then the minimum value that you can get for your V out is 24.3. Makes sense, right? 24.3 nano means that it's almost close to 0. That's the ground. So in other words, your V out swing is actually limited by your power rail. Yeah, either 0 or somewhere slightly lower than VDD. Just now your VDD was how much? 10, right? And then you can go up to 7. That's okay. Let me see your schematic first. Somewhat oh, okay, I see. Okay. Yeah, my mistake there. I just get confused with VDD and VDD over 2. Yeah. So your maximum is 10. And then at your second stage, it should not be more than 10. So somewhat
Yeah,
here,
okay, makes sense.
yeah, but your first stage here, you can actually see first stage maximum is 10.
Yeah.
Yeah.
Mm.
So right now, I think your first stage is 10. Let me see. Why not? It's as if your VD set is actually near to 0, right? Impossible, right? I think because you set the weight to be very high, is it?
But didn't he, for the tail current, you mean?
I mean for the current load
For
on
the
top.
current load.
Yeah, but then doesn't matter. I think what works, right? Yeah, I think it's good enough. So you just need to take note of this. So you can see that you can try to see these two turning points. Yeah, so this means that the minimum VDIP that you can work at is 363 micro, which means that if your V in plus is less than 0, definitely your op amp doesn't work.
Yeah.
Will it be a case where
But it cannot go below 0, right?
let me see. Usually, from what I know, if you do negative feedback, your output will simply oscillate around a certain level that you want. So sometimes it can be higher a bit, sometimes it can be lower a bit. Yeah. For this, actually, I'm not too certain about how they're going to use it.
Yeah.
So later on, from what I heard from the organizer, they say because they observed that a lot of teams, they are not actually, you can see that there's quite a big gap between different uni. So they are worried about this. So I think afterward they do tell me they want to assign their own engineers to work one-on-one on your team, each team.
Oh.
So that they can actually tell you what is the expected outcome. Yeah, in a way. But then on our side, we try to do our best.
Did they say it's us who is falling behind?
No, actually more on the other uni. For example, UTS. Yeah, UTS is the weakest one in the thing. And then 13 is only average. They are not too good, but not too bad also. But then they don't see them as the one standing out. And then Unimas and Swiftburn each is a team that is standing out. Yeah, and then another team which is falling behind. Yeah, we don't care which team it is, but then we try to make it such that and both our
because
team you can just
they have experience with this section.
Yeah. But then we don't worry about them because every unit has different standard. I believe our one has higher standard to be honest. Yeah, so don't worry. We just do our best. And then you try to go to the rightmost turning point. You can see that actually wait. Oh, just now I think okay, because you put vertical, right? This is a vertical value. I think you should go down and I want to see
It's the series.
Yeah, correct. You go to the left hand side first. Yeah, this one. Yeah. 494 milli. Yeah, 494 milli is the lowest VD that you can work with. And then you go to here. This will be about one. Yeah. So 494 milli to 1, about 0.5. 0.5 to 1. Let me think. Audio signal. Perhaps audio signal, they only swing a bit. Yeah.
How much is it like supposed to be theoretically like ideally should be?
Seriously, I think it still depends on how they want to use it. So this range, of course,
Yeah.
the wider it gets, the better. But then if you make it wider, usually there's a trade-off. Make it wider means your gain gets smaller and smaller.
Yeah.
Yeah, that's the thing you need to strike a balance. I think right now your gain is very high.
Yeah.
Your gain is very high, but then yeah, because you see
Yeah.
at 1 volt VDIF, you get 7.6 at about 7 times to 8 times. I think, let me see your specification. The maximum open loop gain is how much? Yeah, that's what we want to see already. So open loop voltage gain is 100 dB. 100 dB if you do a voltage, okay, 20 log. Okay, try to do, for example, you 100 divided by 20 get 5, right? Then 5 log. So 10 to the power of 5, correct? Should be 10 to the power of 5, right?
100.
Yeah, so it's 100k times. Wait, oh, that's the maximum they can give you. So you're still within the range. 100k times bigger, but then you're amplifying by 7.6 at only. Yeah, still acceptable. Let me see. 100 dB. Does it work that way? Let me think first. Did I make any mistake in calculation? 3 dB is twice. Should be 3 dB is about 3 dB is root 2 times. Yeah, correct, yeah. I don't think you violate the rule anyway.
I think maybe this is because the sizing used was the lowest gain or something. I'm not sure.
Okay, minimum gain is how much? Yeah, that's the thing we need to worry about now. Since I see that this is far lower than 100 dB.
Do they have
Here,
then
open loop gain minimum 88. Okay, you try to do 20 log 7.6 at. How much do you get?
17.7.
Oh, 70% actually. Okay, does not meet the minimum requirement. Let me see first. Open your. Okay, I think this is not a right way to find gradient because the graph doesn't start from 0 . We better do it this way. Okay, you take 7.68 minus. Okay, minus 0. Never mind, this goes to 0. Then 7.68 over what? This is 1 minus 0.49. Okay, you just take 7.68 divided by 0.5. It should be around 15.36. Okay, then you put 20 log 15.36. Oh, 23 dB. Yeah, we need a bit more here. Let's see how we can do it so low.
I feel like something's not right. It's a bit too low.
Wait, does it make sense to have such a high gain or not? It's very high actually. Let me think. Large signal, open loop gain. Why do they need so much gain? I also don't understand. Oh. Okay, we start with we proceed first. Then later on we ask them what they think about this. At least we come up with whatever simulation we need. Okay, so let's maybe go back. If you want to visualize this on the transient, we can do that now. Okay, so this is just for you to see how does the first stage amplification vary with your VDIF. Actually, first stage allows negative, right? You can see that.
Yeah.
If your VD is negative, your first stage actually can amplify. Then I will more or less see that maybe the problem is with your second stage there. I think your second stage hit the minimum cap too early already. And then your first, you can see that your first stage, there are two gradient, right? Because there are two poles. One pole introduce a gradient downwards gradient. So you have two poles here. Oh yeah, and then about the margin, I think they ask you to do phase margin.
They said for stability analysis only.
Yeah, later on you need to do some math with it. For example, from what you study in control automation,
Yeah.
yeah, you need to write the equation. For example, the dB dB against the phase. Yeah, that's one thing. You need to use the math function. I think in the tutorial they got teach something. Yeah, just simply take out. I think we go back to the simulation. I think the schematic. Yeah, then we proceed with what we need to do next. I'll teach the one that is not inside the tutorial. Okay, then you want to see everything in real time. You can go back to put in the sine wave now. Okay, to put in sine wave we need to make a bit more changes now. Okay, you can go back first. Okay, right now, what you can do here, well, I'll need you to revert back to the previous step. Yeah. Yeah, here, alright. And now I want you to set this VDC to a certain value you want. Maybe just set it to VDD over 2. Yeah. And then this one you make it set back to VDD. Yes, correct. Okay, now you make this a sine wave.
Analog wave.
Yeah,
It's just sine.
it's correct. Okay, now the DC voltage you set to VDD over 2 as well, meaning that it oscillates at an average of VDD over 2. Okay, then your voltage amplitude. Let's make it, you just put VA, you just put VA. This is your amplitude. Okay, now we will do some sweep.
Chicken sweep.
Yeah. But this is
Okay. You just import all the variables. Okay, maybe you start with one value first. VA you put 1 first. Okay, let's see what happens to your, and then we change, yeah, we do a transient. Yes, correct. And then we do a time step or how fast we want. Okay.
until it's like 0 to.
Oh, I think we forgot to set one thing. What's the frequency of oscillation, right?
Oh yeah.
Yeah, we need to go and, yeah. That one is also needed for your frequency response later. Yeah.
Frequency 1.
Yeah, correct. Maybe we put how much? Sound wave. Okay, audio you can look at
What kilohertz?
different pitch. Yeah, you can go and Google it. Yeah, of course this music is our weak link. We know we go to Wikipedia and then search frequency of different pitch. Yeah. Yeah, music not to frequency. Yeah.
Use that one.
You can use this or you can do Wikipedia also can. Yeah, let's see. So the frequency of our music is from, for example, 16 plus 2
230. Yeah. So
all the way to 7K, right?
The
Yeah.
average is here though. So
okay
for
for
We can put maybe 300. Yeah, let's try 300 hertz first.
okay. Yeah.
But then if you talk about audible range, right? Just last time they mentioned is 20 hertz to 20 kilohertz, right?
yeah.
Yeah, we just put something maybe put a reasonable one, 300 hertz. Yeah, let's see. Okay, so let's run it.
Chicken sweep.
Yeah, later on you notice there'll be more and more parameters to sweep. You might need to sweep the gain against frequency. Yeah. Then you need to make the frequency right in here as an unknown as well. So that you can actually find the frequency response. Okay, maybe 300 hertz. So one period is about 1/300. Should be 0.33 milli, something like that. Yeah, 0.003. So yeah, 3.33 milli, right? So maybe you put one step to be 0.000005.
0.0005.
No,
Yeah, can yeah, this one,
Zero-
yeah, 0005. Then the stop time maybe we put at
0.005.
we don't run to for too long lah, otherwise it will take forever. Maybe put 0.01. Yeah, run for about 3 periods. Okay.
I think all of this should be fine.
Yeah. I think the step size later on I'm scared later on the step size if it's too small then you will take a long time to run Let me see. 0.0005 times 20, right? It will be 0.01. Yeah, I can. Simply means that your simulation would simply plot 20 different points. Yeah, if you make the step size to be too small, you will plot several hundred points. That will take a long time.
The outputs, do you remember?
Then the V out.
Outputs, of the VOUTs.
the VR, you need to make sure that
Yeah,
the analysis right here, you take track.
transit.
Yeah. And then here also V out too.
It's okay.
Okay, so let's start. I find it very weird
Yeah.
Previously, organizers said they should have set out a template for the simulation. For example, common mod game, power supply reagent ratio.
Yeah.
Otherwise, I don't think this is efficient for us We are focusing on design, and then they should have given us the template since everyone does PSRR the same way anyway. CMR also.
Yeah.
Yeah, I don't think.
It's just one is
And oh,
Oh,
it's not
it
even the
click
same.
already. Yeah, I think it's click already.
Sure.
go all the way. So
Okay, what you can do we plot one more thing. We plot the input voltage. Yeah, we can do it. We can do it against time as well. Yeah, so here you click to add, type V in 1. V in plus maybe V in plus V in plus.
VN plus.
Yeah, correct. Then you simply find
This one is.
yes, correct. Yeah, then you DC transient. Okay, yeah, you can.
Yes, sure.
Okay, then we plot again, see what happens. Okay, so right now we can see actually the V out to get 0, right? V out 1 you get a high value. Yeah, seems like it's clicked from the beginning. Okay, let's ungroup them. Let's see first. You ungroup everything. Yeah. Oh. No matter how you oscillate, V out 1 is already at its max.
There's too much gaining.
wait.
I think we need to go back to
Go
schematic.
back to the transient analysis page for the setup. Go back to the setup. Make sure UIC is turned on.
My what?
Go back to the transient setup analysis.
The
setup.
transient.
Setup
Sorry. Okay.
analysis. Go to transient. Make sure UIC is turned
My what?
on. UIC.
UIC, take on
UIC.
UIC means use initial conditions.
Hmm.
Okay, you click apply.
Yeah.
Okay.
Try to
Try
run
again.
again. Let's see.
Just. I close all of this.
Let me see. Why does it not react? I will need to see. I will need to look at the input voltage first. Oh, the input voltage is oscillating around 0. That's why. Yeah, maybe go back a bit. We need to see. I think we need to offset it instead of put a DC voltage. Very weird. I find it very weird. I think we go back here. usually there are some discrepancy in how the person who design the software, how they understand this. I think DC voltage here does not even have an impact, right? Doesn't seem like it
Yeah,
affect-
because it's a transient, right?
I mean, because for any AC, there are DC component.
Yeah.
DC component is average. If I
Yeah.
set it to VDD over 2, then you should notice that the input voltage should oscillate with the midpoint of
Yeah.
VDD over 2, right? Which is 5 volt, right? But it oscillates around 0, correct?
Yeah.
0 is the average. Then I think we remove this. I think DC voltage here, they have a different definition in software. We put an offset. I think offset makes more sense. You shift everything up.
Yeah.
No, we shift by 5 volt. 5 volt. We say VDD over 2. Yeah, instead we write VDD over 2.
This one.
Yeah, correct. VDD over 2. Okay, let's try.
Just one.
Yeah, by the way, the voltage offset here is not the input offset. The input offset, they refer to another thing, which I'm not sure as well. Usually we don't, from our academic point of view, we don't design for it, the input offset or such. We don't do that. Let's see what happens here. Yeah. Then it makes sense already. You can see your input oscillates between 5.
Yeah.
5 is the common mode. Yeah. So we can say offset is common mode. Then we ungroup everything. So you can see that by right, ideally, your Vout2 should be a sine wave as well, right?
Yeah.
But somewhat it gets clicked off.
Mhm.
This means that actually, from what I see is your input VD range is so narrow that
Yeah.
with a small VD, you already hit the cap. Yeah, that's one. Okay. But I'm not sure why they set the design spec to be that strict, which
Yeah.
means the gain, if you want to achieve that high of a gain, I don't think you can even get a sine wave.
You guys managed to achieve it?
The other team?
Yeah.
No, they haven't done it.
Oh,
Yeah.
but
Did
then
anyone even do that?
how does this make sense?
I think one way to tackle this,
We just decrease the gain. What do you think?
yeah, decreasing gain will help to improve the shape of this.
So what if we use, for example, like I said, the lowest gain from here,
Okay, I believe it has
like
something.
160. Is 160.
Yeah, lower tail current does help as well. Yeah, because it reduces gain. Because gain is proportional to your DC current.
Yeah.
And also, let me see. Your first stage already hit the cap very soon. So let me think. I believe that can be also one reason why your Vout2 is so square. Okay, one way we can do, because I do notice that on your current lot, you have 2 MOSFET. 2 MOSFET means 2 VDs that you hit the cap very easily. Yeah, so maybe I'm thinking maybe you can start thinking whether you want to remove 1 MOSFET from the current lot or not.
We can try.
Yeah, you can try actually, because usually I see the 2 current lot as a rather disadvantage to you, because you increase hardware size and then you tend to bottleneck your system a lot. So here,
Delete this.
this one.
Oh, this one.
Yeah, I don't think you need these 2 anymore. Because from what I see, I think your system is rather stable, right? You don't have to have 2 current lots to make sure the current is actually identical across 2 branches. So I don't see that as an issue now. Yeah. In fact, even though they say there's no golden answer to design, but based on the so many limitations they give you, it is believed to be the golden answer for architecture. They already mentioned a few times to us that they said they want the circuit to be too complicated. They want a very simple circuit, so I don't think they will award us if we do the complicated stuff. This means I think folded cascade will not be viable here already. Yeah, we don't try to do that. I don't think we want to go to that.
I just run again. Let's
But it's still be in saturation.
we see this first. I think we can tell from the graph.
Yeah.
Okay.
If this still is click,
Yeah.
that means that
It's
Oh, okay.
the previous I've said the previous width and length that you set needs to be adjusted again. Yeah, that's the tough part about this Yeah, hits the cap source too now. Yeah, the gain I unit is too. Let me see. How do you increase switch on? Yeah, you try a lower tail current first. Let's see what happens.
Hotel curve.
Yeah, correct.
We just decrease the size of the current source itself.
Increase the width of your. Okay, you go to your schematic.
We just decrease.
You're on 40 UA. Right now, this is
No, we can just decrease this.
Yeah, decrease the width of this.
Yeah.
Yeah, 0.1 milli. A bit too much, I think.
Yeah, true. Maybe 1 milli.
Wait, 1 milli is even bigger, right? I think you put
100 U.
what was the smallest width that you can get it to work?
I think this is the maximum I can get it to work, so we can go as low as we want. Maybe I think
Let's try maybe
maybe
80
80.
micron.
Yeah, 80.
Oh, because just now you show me the output, the I out for the current band gap is the one that you get along this line, right?
Yeah.
It's 50 micro, right?
Yeah.
Then it gets multiplied by a lot here. Don't think we try to multiply too much. I think you're going overboard with your current already. Yeah, let's try a different value here. Put 80 first.
We put too much actually.
80, I still think it's a bit high. But then we can try.
If it's too high, we can still decrease.
Yeah,
it.
you can adjust.
Still current we have, right?
I think it's still not working. Check first how much.
Because we're using the 50 micro or so.
8,
Right?
8, 12, 20. 8, 8. Yeah, we're using this one. We're using like very low already.
That's 50 micro, is it?
Yeah, we're using this. So no, it's not 50. It's less. It's maybe like 30.
Yeah, 50 micro is your base, your reference current, right? Then once you mirror it to your main op amp, you actually multiply it further, right? Yeah, I think you multiply too much. Actually, 50, I would say, is a good spot for your current band gap.
Yeah.
It's very good already. Even I would say if you go to, let's say, this is 12.5, right? Yeah, 12.5 is even better because it's more stable. Then later on, you can multiply even further. Since you already adjust, you can adjust your width of your MOSFET to be so much already. Then you just keep everything at your current band gap to your first branch of the current mirror, which means that you go to your schematic.
They were using this one. We're using like the 20 micro.
Yeah,
50 micro seems so unstable.
you can use, I think you can use a 12.5. This one is good enough. Because later on you can go to your schematic.
Okay.
Actually, you go to your zoom out a bit. You go to here. Yeah, your M9. Your M9 is mirrored to M7, right? And then you can see your M7 ratio with 80 to 80. Yeah? Oh, then it's the same ratio, right?
Yeah.
Do I ask you to put the same ratio? Okay, can we put a bigger one?
Yeah.
Let's say this one we put to 160. Yeah, let's see 160 micro. So this one is 0.16 milli, is the same as what you did previously,
The
right?
one I did was 0.18.
Oh, okay. Okay, let's do 0.1.
0.1.
Yeah. We don't try to go too much.
100. Yeah, 0.
Yeah, correct.
Yeah. I tried to run first.
Oh, by the way, your schematic, wait. You zoom out a bit.
Yeah.
Okay.
Is the connection correct actually? This
Hmm.
because actually for me, I'm not sure if this is how you should connect the current source. I just connect directly to here.
Actually, don't have to do that. You can just straight away connect this to here already. You don't need this one.
We did delete.
Yeah, because this is your, actually you go up a bit. Okay, M39 is actually your eye reference already.
Okay.
And then this is your mirror. So you just mirror to this one. You don't need this one actually.
All right.
Yeah, I think this one is a bit redundant.
So
And then to top it off, you have two diode connected. I don't think you can do that lah. Two diode connected. Yeah, you try to remove this line. Yeah, like this. Yeah, that's good already.
like that.
Yeah, correct. Okay.
Yeah, let's see what happens.
Yeah, let's see what happens.
So at this point, I don't know if it's saturation. Let's see.
Slightly improve slightly only. Yeah,
Can you increase it even more?
yeah, increase it even more. Let's see, increase it even more. Maybe in the end you actually don't need that much of a tail current anyway. Maybe
Because they
Yeah.
put the output current in the second stage.
2 mA.
Yeah.
is
So
so
we
much.
increase our tail curve. Right now, what we had was 50 mA, 50 mA, 50 microamps
Yeah.
for around 1 milliamp
Mm.
of output current. But we decrease it to like 40 and 30, our output current will plummet to like 400 micro.
okay. 400 micro, even for me, I think. Okay,
Even
wait.
less than.
They only set a maximum, right?
Yeah,
There's
they
no
set a
minimum.
maximum.
I think we don't have to go all the way to maximum actually.
Because we're like assuming that the maximum, somewhere close to the maximum
It's
is
the
what
best
they want.
lah.
It's what they want.
Actually, no.
Because
Because- Close to maximum means you consume a lot of energy, a lot of power. Yeah, usually the lower the better.
I see.
They
Yeah.
want lower.
Just stable, more stable is better, I guess.
Yeah, correct.
40 or 60, 60U?
60, yeah, put 60.
60U.
2 milliamp, if you have 2 milliamp current, I think your power is quite large for a microchip already.
It's gonna use our pain.
And I think in layout terms,
Yeah.
Derek
Yeah,
told
you-
me it's gonna be
You
very,
need a very,
very thick.
very white, very white metal to conduct. Yeah, still, okay, I think, wait, for the first stage, how can we improve further?
I'll just want to check if it's in saturation.
Okay, sure.
PC operating point.
Improve the results.
Oh,
Okay,
This two are linear.
okay, let's zoom in first.
These are cutoff actually.
Yeah, okay, let's zoom in first. Let's see. Would you be able to get the voltage here?
Yeah.
Let's see.
10.
10. 10 volt here. How is it then? Oh, because this is cut off.
Yes.
Okay, let's go in here and look at here.
How come this is cut off? Wait.
You zoom in first, you see this node V in plus.
Well, V plus is not even here, isn't it? This is V plus.
Or maybe
Maybe because it,
swings, right?
yeah. So it starts at zero.
Okay, maybe this one we switch back first. You put a VDC now. Okay, this one you can drag out and then you put a VDC here so that we can check whether, because right now because we are setting for DC operating point. So this one is in AC, so very hard to tell actually. Yeah, you try to remove this, then we check again. Yeah. Yeah, put back the DC here. Copy and paste it. Yeah, same thing. Okay, now you run the DC operating point again. Yeah, you do the run again. Yeah. Okay, just ignore this.
Yeah, yeah.
Okay. Yeah, everything is good now.
No, this
Just
one
the
is
one,
better,
yeah. Okay.
I
so
think because it's too hard, too large, this one is maybe because this one also I need to decrease a bit.
Okay, Okay, Samuel. Yeah, I think he needs to leave now. Never mind.
Oh, okay.
Yeah, okay, let's look
I
at this.
decrease this one maybe to
Yeah, the
60 as
VGS.
well, or 80. 80. Because this one is already like a milli.
Okay, then. Just now, this one was how much?
It was 180.
Hmm.
180.
It was the same as this. Not
Can you
really.
annotate the voltage here? I want to see at DC mode.
Yeah.
So low. Only 2 point something.
Mm.
Okay, slow down a bit. See. How much is this? See, right? 1 point. Oh, okay. Oh, the figure is very low actually on DC. Hmm. Okay, we move this. I think you can go up here. This one. Oh, you have another.
Yeah.
I don't think you need this one. I don't think you need this one. Yeah. Yeah, remove it, remove it. Yeah, this one no need already. Because this introduces a drop in VDS and another one introduced by this one.
Yeah, let's see.
Let's see first. Let's see first. Try to run again, then we try to tune. I think it does not solve the problem entirely. We need to fine tune again.
Still.
Okay, you annotate the node voltage. Okay. Let's zoom in a bit. The VGS here is quite high. One reason is because, let me see. Go up a bit. So now I'm see this one, the width for this one. Same width, right?
Yeah.
So 7.8. Wow. Your VGS is very, oh no, VSG, right? VSG here.
Yeah.
VSG is about 2.2. Then the VDS is very high. This is very low actually. Why is it so high? Let me think. Let me see. If we, how can we make this smaller?
We decrease the width of this one.
Yeah, possibly.
Lower width means less current.
Lower width means larger VSG. And
Then
then
the
actually
voltage
this one VGS would be higher as well because, wait, let me see first the ratio. Okay, go down a bit. I want to check the other one. Yeah, this one. The VGS for this one is about 1.9722. I think this part is too low.
Yeah.
How can we improve it on? Let's see. Right now, your V in equals to V in plus equals to V in minus. Okay, you go to the left hand side. I'm going to see the first stage. Here, 7.8 still the same. 7.8 here. Let's see. This is high side. Okay, let me think first. Hmm. How long?
but we haven't done the actual transient yet, or which one was it?
You mean
The
what's it called? UET?
no, I mean the to check the offset visit.
Check the offset. You mean the first one we did?
Yeah.
That one is for transit.
That when we pro with the last MOSFET there. This one is in very deep saturation. Can we push it further? Push it. I mean, push it nearer to the triode. Because this one is way in the deep saturation. I don't think this we
You
need.
can decrease, I think. Maybe
Yeah, you should try to decrease a bit. Let's see.
118.
maybe 80 ATU.
Yeah, ITU. Let's see.
I think this should work. I think this should work.
Okay, let's see.
I'm still.
Okay,
But,
we see the voltage. Does it improve or not?
Not really.
How much is this?
0.
Still very low. Then this voltage is still the same. Yeah, doesn't
It
change.
wouldn't change anything. Yes. Zero.
Doesn't change actually. You see, I think it is not updated. And you try to change again.
Yeah,
Yeah.
I just changed it actually.
Or change it back.
Yeah.
Oh, okay.
What if we increase the NMOS?
You mean
This one, maybe if we increase the width.
okay? Which width?
But or can we add another NMOS?
I don't think you can do that in second stage.
Yeah.
we go ahead and talk about this.
Yeah.
Just now when we have VD is 0, you get this one to be triode, this one to be saturation. And now when you go to VD to be 0.5, you get this to be triode, this one to be saturation, right? This means that your V out now hits a maximum cap. You can try to annotate the voltage here. Yeah, it will show you lah. Now it's 9 point something already hit the cap.
So it's a zero, either zero or
Yeah, it goes
it's like
so high.
square
Yeah,
wave. I think this is part of the problems. So
I think this only signifies your working range.
yeah,
Yeah, just about the working range. Why this is in triode? Because this is inverting. The VD is so high that this goes into this voltage is very low, hits the bottom cap. That's why you see a square wave like shape. I think your whole system is working perfectly fine, just that the range is a bit tight. Yeah, very
how
tight
do we
range.
actually increase them?
Yeah, how to increase range? You can Google first. Yeah, the best way is to ask Google actually.
What should I say?
What do we call that?
Working.
How to increase working differential? Wait, how to increase differential voltage? Working range? I will just simply type one working range for op-amp. Adding a voltage divider at the input to shift the common mode voltage and put it rail to rail op-amp. You click show more. Yeah, okay, from my point of view, the easiest way to have a wider working range is to make the gain smaller. When you make the gain smaller, actually you notice that if I make the gain smaller, it's harder for my output voltage to swing that much, right? So it's less likely to hit the cap and hit the minimum.
It takes longer to.
Yeah,
swing,
yeah,
right?
correct. Yeah, so you can get a wider range. So what I'm saying is, now you try to do one thing, a very extreme one. You try to make, yeah, means you try to reduce the weight here, not
20,
okay. You put 15.
50.
Yeah, the very extreme case. And then this one you also change. Yeah, correct. Maybe you change it to let's say just stop at 50 or 40. 40.
And this one stays.
Also 40. Yes. I still think it's quite big also.
It's
Yeah.
Because but then this one is gonna be like
Yeah, we
yes.
can you need to tune anyway lah. So I think at this point of time we want to make the thing work as best as possible. So
yeah.
yeah, we have to tune it anyway. Yeah, so previous actually when you show me that when the V in plus and V in minus, they are all at common mode lah. Actually, from what I noticed, now I realize it. At common mode, voltage for both sides, you just need to ensure your tail current MOSFET is in saturation. That's it. For this part, actually I won't be worried about it. Most likely is you are hitting the cap or hitting the max or min. Yeah, so you can see actually everywhere other than your output here, the rest are all in saturation. That is fine already. The only three MOSFET that are changing are these three, right? This depends on your VD. So if this two goes into triode, means that you are hitting the max again.
Okay.
So this one I think is still too high. So let's make it much smaller, maybe
20 as well. Because this one is 80, is it? Like 60.
yeah, I think this. Okay. If you switch this to, let's say, make it 40. Yeah. So 40, 40, 40. Let's see what happens. It's 40, 20, huh? Okay. Yeah, 40, 20, 20. Okay, you can try this.
20, 20.
Yeah, this one 20. Yeah, yeah. Okay, let's see what happens.
I think at this point the gain doesn't really matter. What matters is the
Yeah, right.
making it
Yeah.
clipping. Then it will almost
Yeah,
not work.
clipping would not. Yeah, clipping is like you are not sure how you're setting a speed limit to your car, and then yeah, you somewhat cannot do much lah.
Would it
okay.
be this, right?
Yeah, these
This-
two
yeah,
you
it's
can
too much.
try.
40.
Yeah, you can try reducing the ratio. Yeah, correct, correct.
This should work.
What I know is for the current lot, usually they prefer a longer length lah. But then they ask you to put the same length for everything, right?
Yeah, for the
This means that we just simply make the ratios. Yeah, put 20 first lah. This one change. Now the question is that what is the expected amplitude of their audio that I send in? If that is not that big lah, I don't think it's a problem lah. For example, maybe you don't put 0.5 now, you put a 0.1. Let's see what happens.
0.1.
Yeah, 0.1. Go back here. Go there. Let me see.
Review.
You go to
back to your schematic.
yeah, back to schematic. Yeah.
And then to your power source. Bottom left. I think we change to
Yeah, change to 0.1. Let's see what happens.
I mean, this one.
Yeah. Perhaps this is a question that we need to find out. I think at this stage of time, maybe since we know how to do this analysis, then I think that's fine for now. Later on, we need to get some guidance from the organizer. Let's see the voltage again. Let's see the node voltage here.
That's the max.
I think very the voltage is a bit small lah. Yeah. Okay. Since we know this, okay, never mind. Let's run the DC strip that we have just now. Okay, right now you put here. This one, okay. You put a VDIF at 0.1 here. VDD over 2 plus 0.1. Plus VDIF. Yes, correct. Okay, right now. Okay, that's fine already. So right now we go to the simulation. Yeah, I think just now lah.
Yeah.
But by setting up this, you don't have to change the connection lah. Then we just say VDD over 2 plus VDIF instead of reconnecting everything lah. Put a VDIF in the middle. Yeah. So this one we change it. We sweep it lah. I think we sweep the same way lah. Yeah, can. This one you run again.
Just run.
Yeah, correct.
Maybe we're running -5 to 5.
Yeah. Okay, now we see the graph again. So in this case, to save time, we don't keep running the operating point. Since we know operating point is already, I say, good enough lah. Go DC. Yeah, now it's transient. We don't care. Yeah, this one. Okay, V in. Okay, of course, V in increasing with V in. No difference. And then this one, yeah. You can see this is the part where yeah, right now actually you see by changing the By what? By changing some of the width, you actually manage to shift it to from negative VDIF to positive VDIF. Actually, that's good already, because sometimes your V in plus can be lower than V in minus. That's when you want the system to tune it back, right? If you do negative feedback. So if you only have the working range in a positive region, then your system will likely not work that well.
Yeah.
I think it's if this is the case, this is good. Maybe now we can see there are two poles. Let's try do one thing. You add the compensator, the compensation, yes. Yeah, this one very easy. You just go back to your schematic, just add one capacitor, that's it. I think they have the library for you to take, right? Yeah, you put in the capacitor here. Yeah, mirror you just put here. You connect the V out 2 to V out 1. Yeah. Usually you connect compensation between the input and output. So this is the input, this output. You just put it here.
Yeah.
As those CSAN WTN. CSAN.
C send.
Yeah. Could find it CSAN.
You're using private light, man. Or this one.
Are you sure?
CSAN WTN.
Yeah, correct.
CSAN WTN.
Looks weird. Why it's 3 terminals?
Yeah, I think this one, I think they use it the same way. You tie it to ground or maybe.
We never tried this. We never tried the capacitor.
Okay, when you connect first. Yeah, and then this one I think need to tie to ground or VDD. Maybe since
Ground.
they tell you VDD, you try VDD first.
Really?
Yeah, I try tie to VDD first. Yeah, and then this one you change the value of your capacitance.
Oh, it has multipliers.
Oh yeah, they said we can use the multiplier.
Yeah, well, you can only use the multiplier to control the.
Yeah, I think that this is smallest unit they can produce. Okay, just put 2. Let's see. Yeah, I don't think you need that much of
Total
a.
capacitance will be 0.5
Yeah.
pico.
Usually they do it in pico. I don't think they go to so.
Yeah, pico is good enough.
Yeah. Okay, just put 2 first. Okay, let's see what happens now. I think it can somewhat, I think, helps with the pole. Helps with the double pole, but then let's see. Let's see. Yeah, we see the waveform straight away.
I think you should be connecting it to ground.
It went
To
to the
ground?
negative, right?
Okay, let's connect the
Connect the capacitor to ground.
capacitor, the third pin to ground.
From what I'm reading, it says connect to ground.
Here. Still nothing. Oh, yeah, this one coming. Go to DC. So many graph. Oh, this one I out, I mean. Yeah, just delete first. A bit of smooth surface.
We increase the capacitance.
Yeah, you can increase it. And then
Maybe
for
too
this
big.
part, yeah, for this part, how do we even widen the range of make the tail current smaller so that
It's smaller.
yeah, this one is actually we have to at this point I also cannot tell what is the golden answer already.
What is this range called? Like what they call it?
Oh, do you mean the horizontal range?
Yeah.
Yeah, actually, we just now Google it. Seems like it was called the differential voltage operating range. Yeah, the range that you can work for a range of differential voltage VDIF. Yeah, so apparently your working range is between maybe negative 0.
But if it's the smaller, the worse actually.
Yeah, correct.
It's very small. And by decreasing the gain, you have like longer range,
Yeah.
reach the maximum before clipping.
Okay, this actually is a good question for them. When's your sync up session?
Tomorrow.
Tomorrow?
No, it's when Thursday or tomorrow. 3 p.m.
Yeah, you can seek their advice is what parameters can we tune to increase this further? From the industrial point of view, they would know what to tune. Yeah, usually they have a certain standard to follow. Usually last time, I think we did something somewhat experiment like this, but then they already give us the value for it. Usually, yeah, it looks almost like this anyway. They will just say if you tune the gain to be higher, you likely get a smaller, tighter region.
This is what it says about that one. It actually says to increase instead of decrease.
Increased tail current.
I don't know if this is accurate or not.
ChatGPT, yeah, sometimes it can be. You can try that. You can try that. Oh my god. Increased tail current. Okay, from my point of view, I know increased tail current, the gain gets larger, the easier it is for you to hit the maximum. Yeah, it's like, for example, you have a graph that increase with this gradient.
Yeah.
Because the steeper the graph, the faster you reach the top. If
Yeah.
you make it less steep, then you can actually have a wider region, right? That sounds more logical. Actually, that's how it should behave.
Does it involve like resistance?
Other than having, let's say there's another way you want to have a wider region you set VD to be 15. That's the widest you can get You can try you can try set VD to be 15, then see what happens. Because now you're operating at 10 only. Yeah, 15 VDD here. Yeah, change it to 15.
Just run it.
Yeah, just run. Okay, go to DC. Oh, same region actually. Yeah, you still hit the cap within the same region.
I'll try to increase the capacitor to see just
Yeah,
maybe it will increase the
yeah, can.
say 20. It's already 5 pico.
Can try.
See what happens. Because capacitor can delay, right?
Yeah.
If we delay, maybe this can cause the range to be greater, maybe.
Capacitor in a way also acts as a way to actually separate your output resistance from your input side in a way that's what they say Apparently there's no difference, right? Yeah, actually I think the capacitance is only observable. The effect is only visible to you if you do transient.
Yeah.
If you look at the sine wave.
Oh, this
Right now
is-
we are doing
Oh,
everything
see,
DC. Yes.
Okay.
Yeah, this is a question that we can ask At least I would say at least the good thing is look at the bright side
Yeah.
The way your MOSFET behave it's just like a op-amp. It's op-amp already
But
Yeah, correct. Just that you need to work on the range actually agrees everything. Or you see the shape, it's like a mirror, right? Because this inverts once, then this one inverts again.
At least I'm glad that everything we're using right now is actually not ideal, you know.
Yeah.
Everything is not ideal and it works like that. So that's
Yeah.
good.
Yeah, it works already.
I
Yeah.
think one thing we can do is just try the different current sources. These.
Yeah, actually, I see just now the range is also as wide as this, right? Initially, when you
Yeah.
when you have the range between 0.5 to 1.
Yeah.
Yeah, this one is also 0.51 or 1, 2, 3, 4, 5. Okay, so it's 0.4. About 0.4 to negative 0.4 to 0.4 of that Yeah, similar range similar range. The range actually declines by 0.2 but I don't think that is significant
Well, we just try to change the tail curve.
Yeah, you can try. You can try. You increase the tail current more. Let's see what happens. Usually we do like this. Yeah, it's bad to be conservative. Actually, you need to go to some extreme cases. Increase it to extreme and see what happens. If you think, okay, let's say increase to extreme something good happens then you know
To both, right?
Yeah, to both, to both. Yeah, I think we will do some final testing Then for CMRR and PSRR, okay, PSRR I think can be achieved through DC, and then common mode rejection. I believe there's an equation that can write to calculate dB. Oh, yeah, there's an equation.
Is this better? I think
It went back to 0.
This
Is it
part
in-
is quite promising in one way. It's more curvy, right? But here, I think still
it's the second
gets
step.
shifted, right? I think
It shifted to 0.
we can see that actually the gradient here is very small. And suddenly it becomes very big. I think there are two. No, I cannot say it's pole, right? Because you are plotting against V in. Not, I think not pole actually. Somewhat like you increase the V into this region. I think one of your MOSFET starts behaving right already. Yeah, I think actually the region is here. The working region is 0 to 0.4. Yeah, actually it declines, right? When you increase V supply. As the I tail.
Tail curve.
Maybe make it much smaller. Let's see what happens.
You can change the width to 4. That's the minimum.
Yeah, we try to change it.
Try to quick.
Yeah, it is at this point we just try what we can. Yeah, for you.
It's the original.
And to be honest, actually I recall some of the values they said they don't go to this large of a width. Yeah, from what I see,
They told us to use very large size. I don't know why. More for the high driving, current driving.
Yeah, I just keep saying that you should always keep the length. If industrial, it's always best to keep the length stable. If you need to increase your width, your last hope, if you can do it, is just increase the length if you can.
It only changes the first stage, I think.
Yeah, improve by a bit only. At least it's just now was 0.4 working range. Now it's still about that, right? Still the same.
The gain is probably like at the 200 or 100 microphone.
Okay, one thing we can do now instead of changing tail current, you can change the MOSFET connected to V in plus and V in minus. That's the first stage of the amplification. Let's try that I think that will actually improve Okay, one thing we can do maybe we'll make the gain smaller for these two. Yeah, these two. You try to put add. Actually, at this point once you can see the graph you don't even need to see the operating point already. You more or less know already Wait we decrease the weight by so much already. Yeah, the gain is
I
still
don't think anything in the schematic changes this. Not sure. Maybe we have to add something.
that's previously when you put two current dots also doesn't, it's not any different from this, right?
So already
Gain is so high actually. What's the gain so high? I mean, to be fair, I think the gain is very high. For what I can see is perhaps 0.4 is good because what I think is maybe the audio signal is only with the amplitude of BVM, millivolt.
Oh,
Yeah, because the volt if the VDIF is only in a few millivolt, then this is a good range already. If let's say we can shift this linear region a
yeah.
bit to the left hand side, make it balanced, then it would be great.
we already did that, right?
So we want to make this thing move a bit.
Yeah, to the left.
To the negative. you mean. So
Yeah, right to the negative side.
What wasn't it in the
What's
negative?
already in the negative side?
Yeah, but this region is a bit.
Yeah, still in the positive.
Yeah, if we can have a constant gradient on our most common working region, then will be best Yeah, from what I see I think actually in the real amplifier, I don't think the VD will be that high. It will be very small Just now, okay, I lost track already Just now when we increase the gain to be very high, does it actually help to make the graph steeper near the
Let's put it back to 200.
Yeah, go back I think.
Yeah.
Since we know decreasing doesn't help in any way, right? Since they want higher drive current, then
We
Yeah.
change this back to
high value. Yeah,
Okay, then go back to that. So
just what's the
yeah, 40. Let's make it 40.
sports again.
Yeah. Then your tail current, I think, can increase back.
To 200.
what's the maximum we can put?
200. Isn't. I think so. Go for it.
Okay. Let's try.
For the max, I think the maximum is like 500.
Since they like very high width, very big width, then we just go max see if I have those. Okay. Now we see some improvement already. You can see the gradient
It's
along
negative.
this line is a bit less discrepancy, right?
Oh, okay.
Okay. I think this is the way. This may be the way.
Increase the current that
We
much.
we can also actually, by the way,
Then you are correct with that. ChatGPT is the correct answer, right? Somewhat. Or maybe just now when you increase the gain of these two.
yeah, because I also changed these ones.
Okay.
So we increase this one too.
Let's increase further. Let's see what happens.
80.
Yeah, let's make it 80. But increase again, that's why I cannot quite understand but let's run it first At this point, I don't think it's worth thinking too much just
Yeah.
run it, and then we just do backward engineering thinking. Okay, go back to DC.
Nothing much.
Okay, nothing much, right? So the gain
We can
doesn't
do
help.
something as well.
So it's the tail.
Yeah, tail
We
current. Can
use
you?
the current source.
Yeah, can you try to?
Use the one where because right now we have this one. Maybe we can use
Do you want stability or do you want?
if we use this one, that's how it should look like. Maybe we can use this.
Yeah, use this one. Yeah, use this one. 9, 10, 12, 26, right?
Please.
For tail current of how much? 40.
400. 0.4.
Okay, okay.
Oh my god.
Yeah.
Okay, shift too much to the left, too much. I think tail current affects the shifting in one way, right? Okay, so let's,
Maybe we just decrease the tail current from here.
yeah, correct, you can do that.
We decrease these two
Yeah,
because these are maximum. So
Put at 300.
before, right? Was it like how they
You put at 200 before you put it at 200.
200?
That's half.
I think the one on top you also need to change. Yeah, this one.
How much?
Yeah, make it same.
200?
Yeah,
100.
wait, let me see. Usually they would say, okay, 200, 200, right?
Mm.
So split into half. Okay, this one, for what I learned is, there's a rule where, let me think, because this is for matching purpose. They say, okay, let's say you have, okay, I said this is current I. This is I over 2, right?
Mhm.
And you have I flowing through here, right? So the current through this MOSFET is twice the value of this. If you scroll out a bit, go out a bit. Usually they say the width of this should be in the same proportion. Means that if you have double current here, the width here needs to double this. So
It's 20, so 40 maybe?
yeah, 40, try 40 for this one. Yeah. To provide good matching, is that's what they say. Yeah,
Okay, let's try.
try it first.
Control.
Yeah, I read it from another book. They mentioned is matching purpose. Okay. All right, all right.
Is this?
Somewhat quite nice already, right?
I think the range also increased, does it?
Yeah, increase. I think this is good already. Maybe I think because if you look at it, the audio signal, how if you look at how we implement the negative feedback, would the audio signal differ from our output by that much actually?
Oh.
That's one question cut off
Not often all of these are linear.
Linear.
So
but then
Yeah.
this cut off refer to which value? Because we are sweeping, right?
yeah,
I think we
not
are
sure
sweeping
because-
here maybe you go back here. I think you go back to the graph.
Okay.
I think they're referring to the first value you put in. You go back to the graph.
Yeah, yeah.
Wait, the waveform.
Yeah, you should.
Yeah, the first V in you put in is -5. So -5, I think everything.
Yeah, yeah.
I think
that's
that's
right.
cut off
But I don't really think we should worry about saturation.
Yeah.
Worry about this.
Yeah, I think if you can work along this region, it's saturation already. Because
Yeah.
at saturation, your V out increases linearly with V in.
Yeah.
Yeah, that's the region you're looking at. Yeah, just that the first stage doesn't seem that nice, but then you see the second stage quite nice already.
I think this is what matters the most. Is
Yeah, and then good thing is your first stage doesn't hit the cap, doesn't hit the maximum that quickly. Yeah,
I see.
that's good thing to see. I think it's quite nice actually. Good improvement already. Yeah, the next step will be asking them whether is this range good enough.
Yeah,
Or
I think-
what you can do is instead of showing them the big range, you show them big range and you zoom in a bit. Let them see if you zoom in a bit, maybe. See, should be here. Yeah. Okay. Here I think. Yeah, zoom in like this. Oh, macam feels like quite wide, right? And then only then you go all the way out. Yeah, only then you go to full view. It's like this. Yeah, you show them the middle one first. Yeah, like this. Yeah.
Yeah, should be.
Yeah, this sounds like looks legit, right?
Should be.
Yeah, and,
I think it's already one. So from -5 milli to
Yeah.
that's 500 million.
500 milli still.
yes,
Still.
negative 500 to 500. So it's one.
It's pretty much one.
One.
Yeah.
Yeah, and then in the audio, I think in audio, even millivolt difference is, I think 20 or 30 millivolt is quite big already. I think of the difference lah. I think this is good lah.
You can ask them.
Yeah, if they want the range to be narrower and gain to be steeper, then we can change again lah. I think just now,
You just play around with it.
Yeah.
yeah, the tail current gets smaller. I think the range gets smaller, right?
The tail current gets smaller, the range gets smaller, and the down increase.
But then it's weird. You decrease tail current, then the graph gets steeper. Is it?
It gets steeper by 15 points. What value is this? Because just now previously it was 7.68.
Also same. This one also 7.6 from what I see lah.
Just to hold
Yeah,
to
pull the cursor. Go all the way to the right.
This one.
7.24. Okay. This is when you have a lot of tail current, right?
this is a lot of tail current. Very, very big tail current. But this has a lot of tail current.
Who can explain this on? I'm actually also at the start now. Yeah. Because I read some books, I try to find answers to all these phenomenon.
Yeah.
They say the best way to do MOSFET design industry is by simulation. They said you just brute force all your
I
way.
don't know why. It's just
Yeah.
you-
Because I read a lot of books, every book they have different way of explaining. That's why they a lot of people I don't think they understand this fully, but then they try to explain it their own way.
feels very like it's a lie though. You increase tail current, you also increase your gain, but then you
Yeah.
also make this wire it's like only good, not bad. Feels like something is wrong.
Maybe the only bad thing is the
Yeah.
gain somewhat gets smaller. I think the cap, the
cat sound
swing.
gets smaller. but
Yeah.
The effect seems very minimal though. It decreased by 0.4 volt.
Maybe there can be other issue because just now we do not only change the tail current, right? We also change the width of the top MOSFET.
Yeah.
I think the stage 2 we try to change the width again. Let's see what happens. I think that affects.
How much should I?
Okay, you make it much larger. Let's see now this one. Yeah, make it much larger.
Maybe 200, same as this.
Yes, can you try?
I'm gonna
But you said also that it has to be.
This is for matching but then if it's not properly matched, I think it's no big problem no big deal
要1包还是2包？2包哈。
可以一包是没有调味料的吗？家里没有哈。
人家讲1包是没有，它是 original 没有任何调味料啊，我看也没有。
Okay.
Oh no, you have to zoom out.
You put this one zoom to fit. This one also can. Okay, now
We moved it to the
so by tuning the top MOS,
Also
can
can,
move the position of the
but I don't think it changes the range, is it? So here is -2.5.
yeah.
Here is -2.
No, it does.
decline, right?
Change it to.
It changed it by 500 millivolts. So yeah.
It's half already
So
Yeah.
it goes back and also.
against
the
zero.
bad thing.
Yeah, so that's a bad thing,
You
right?
need to make it lower.
Yeah, the
So
width
we
needs to be
decrease the-
lower for that one. Yeah,
Okay, so we just
make it lower
you
now.
made it 40 U. Now you try 4 U. Previously it was 40 U.
So 100.
You try 4 U. 4 U. You try to make it as minimal as possible. So that's the 10 times smaller.
No, I mean when we do layout, this is. I don't think.
Yeah, but it's just for testing.
Yeah, just to see how it changes. Yeah.
logically it will move to the right because
Should
by
be.
increasing it, you move it to 0, and then now you move it more to the right. So you need to zoom out.
Oh,
Yeah.
VCD.
This is.
Oh, this is
Okay.
oh no. Oh my god.
Well, what is this?
Just now you changed to how much?
For you.
For
For
you.
you only lah.
So this now makes it
有啊，所以呢，
Somewhat wider.
两包一样
In a sense, because it's still increasing, Yeah, hasn't reached the cap yet. You try to drag to all the way to right. Oh, but you see, the maximum swing. Okay, go to the right. The maximum you can get is only 80 millivolt.
Okay, so
Yeah.
there's a cap which you cannot exceed.
Yeah, you cannot decrease it too much. You have to make
Yeah, yeah.
reach a point.
It's the balance, maybe. How much was it in the first?
40, I think.
40, so maybe 20.
Okay. Right now, if you want to save time, you can also do one thing. You can do a nested sweep now.
Yeah.
While you are sweeping the V in, you sweep maybe you change the width of the top MOSFET, that one only lah. You give it a value like WN maybe. Yeah, you go back to schematic, then you can sweep. That one should be parametric sweep already, right?
Yeah, you can get
W1.
WN,
W1,
yeah.
W. WN was better.
Yeah, then
Make it less complicated. I think you only focus on one graph. So you get rid of VR1 and
yeah, I think VR1 you can just untick all.
and VR and V in. So we just focus on VR2.
Yeah, correct. Just focus on VR2.
So this and then you go to parametric sweep.
What is that? Can you?
You can first do let's see, variables, from design, vector, etc. That's analysis. Where is it? I can't remember.
I think it's not here. It's somewhere.
Wait.
You can refer to your phone,
Right.
I think.
Yes,
Yeah.
correct. This one, yeah, sweep. Add one sweep first. Yeah, you add the sweep of VD first. And then on top of that, because I think it starts with the first being the priority. I
Yeah.
think if you sweep the VD first, it will plot the V out against VD. Then when you put you can arrange the sequence later on, no worries.
I don't like
Come on, we want to
This one you put
for you to. I think we don't need for you.
just now, how much you can reach? 200 U, right?
Yeah.
For you is the worst section.
Yeah, you put to 200.
100.
Yeah. Then we put the steps. Okay,
Maybe 10.
you change this one to steps.
Yeah.
Or you can choose total points also lah. Total points means how many graph you have to see. Maybe you change total points. We don't care about step size anymore. Yeah, maybe how many graph you can see at a time? 5.
I think 5 is best.
Okay, put 10 lah. Put 10.
10.
Yeah, put 10.
7用完的。
Okay. And then this one you go back to the parametric sweep.
Okay. The metric
Yes.
parametric is what?
Add one more sweep. You add the diff, P diff. Yeah, you swing from -5 to.
No, but this one we can
Oh,
just use the.
already, yeah, correct, yeah, no need. Yeah, correct.
So you should
Yeah, okay.
Okay.
Okay, now let's run it.
Then you put that.
Yeah, just now we changed to WN. Yeah, I think this one will run for the last round now.
Yeah.
Afterwards, you can try to play with the value. Then one day we may need to come back to work on the common mode rejection ratio of the DB.
Yeah, but how can, I think it's too fast already for them to move to front end.
Yeah, DB I think only is important for the phase margin and also
Gain margin.
gain margin. Yeah, I don't think we need DB for common mode rejection ratio. I think for common mode rejection ratio and also the power supply rejection ratio,
Yeah.
you just need to try to swing the power supply and see how much does it change. Yeah, that's it only. Yeah, if it remains constant, then so be it.
I think that's
Yeah.
the most we can do.
Yeah, correct. I don't think they ask for phase margin or anything. Yeah, that one later. I don't think we need that.
So
What is this?
this is
See.
trend. What does it mean?
Yeah, this one. Yeah. You try to click on the plus. Click on the plus there.
What?
The plus sign. Yeah. Yeah, it will show you. You try to drag this. You try to enlarge this. This tab.
Okay.
Yeah.
Okay.
Okay, you can do it. We can see to get too far.
Yeah, correct. Then they will tell you when WN equals to different colors. So the more you increase, the more it goes to the left, right? And then
Oh, at one point it completely drops.
this is at U. Yeah, very small.
I think the orange color.
Yeah, the greater the width, you get the higher ceiling. But at the same time, you get it to shift more towards the negative side. So actually, you look at the most the most balanced region
50U.
could be 50, maybe need to be below 50 or
Below 50.
if 50 you get a much better at the positive side, maybe 25 or then we can make the sweep narrower now.
So,
Swing from 8 to 50, then we put 10 points off.
oh, this is 30 actually. 30U.
Mm.
30U to 50U.
Then the swing or the ceiling is much lower. Yeah, we can try to swing it.
Okay.
50U.
Mm.
Yeah, 10 points. Good enough. Yeah. Yeah, now this is another way you can do to make your simulation much faster now. Everything on the pipeline, just run it. It's going to be
2U difference between each of them.
and then I would say parametric sweep, you went into the second level good enough. You went to the third level, the number of graphs you see will multiply a lot.
Yeah.
Okay, try to expand the view. Yeah,
Okay, so now it's
you can actually click, you can hover your mouse here, then you can highlight, this one.
this one. This one. These two.
Okay, between 38 to 41. Hey, just now seems like 40 is the best, right? You just came out with 40.
Yeah.
Yeah.
And 40 just gives you negative 0.5,
Yeah.
0.5.
Maybe the next step, since you know it's 40 already, then the next step is how do you make it wider by tuning other values? Yeah. Then the other MOSFET, we need to go through the same process.
Yeah.
Okay,
You just keep it 40.
yeah, keep it 40, then time to tune another MOSFET.
Let's do 40.
Yeah, this one 40. Now we can shift the WN to another MOSFET. Maybe you can turn your attention to M12 only. Yeah. Then time to do the same thing.
Run the trans.
Yeah. Maybe you can try a wider range when you get back. You have the time now. Yeah, just control.
Just check and see.
Yeah, go back to your
Command.
thing.
I changed the
Yeah.
sweep.
Yes, you change the sweep. Now for wider value now.
From how much to because
back.
it was very, very large.
Maybe go back to from
100 to
10 to 100. Yeah. That looks reasonable. Yeah. Now everything looks promising now. Yeah. I think very likely your group will get everything to work.
Bullish. Really, really focus.
After this, what should we do next?
After this, maybe not yet. The power supply restriction ratio. Maybe no need to count the ratio. You just see if you sweep the power supply, how does keep everything else. For example, maybe the VDIP to be constant. Then you see the power supply. You sweep it. Or what you can do is, I know. What you can do later is you change the parametric sweep. You change to VDD.
Yeah.
Then you produce 10 different graphs of how the V out corresponds reacts to your VDIP. Now you have the V out against VDIP, right?
Yeah.
Instead of plotting it with, you have 10 curves that correspond to different VN, WN. Instead of doing that, you change it to each graph corresponds to different VDD. Yeah, if let's say all the 10 graphs, they are completely the same as one another, means that your system is completely resistant to power supply change. And that's one thing. But I doubt it will be completely the same because by changing the power supply, you're changing the maximum and minimum cap.
Yeah.
But as long as I think the gradient is the same, that's good.
See.
Yeah.
So really constant at 50 to 80. 50, 60, 70, 80.
Yeah.
Very small change here, but a very big change.
This one is good, right?
Yeah, so it's the one we have as in 40.
Yeah. Even though the ceiling is lower, but then it looks quite good.
So it's 0.5. Can you do the cursor then?
Yeah.
Increase the width, the ceiling gets lower.
Yeah, see from negatives 400 to 400. That's right.
73.
Yeah.
Negative 0.5 to 0.5.
Then you see that why we increase the width of the bottom MOSFET, the ceiling gets lower.
By the way, we just changed like only one of the NMOS, not the tail as well.
Yeah.
Only should be.
If we increase the NMOS width, we are indirectly increasing the tail current.
Yeah.
For second stage.
Yeah.
Then the ceiling actually decreases. Okay, let me think first. Increase the width. You can only hit 8 volt maximum. But why is it so? Very weird. Never mind. I think that drain voltage is a floating voltage, so very hard to explain anyway. Okay, try to expand this. I want to see the. Oh no, actually, the other way around. When you increase the width, the ceiling gets higher.
Yeah.
Yeah. You decrease the width, the ceiling gets lower. Yeah.
Change the range gets much.
Yeah. The floor is still more or less the same. The ceiling gets changed. But what makes sense? Does it make sense? Yeah.
They're not supposed to make sense in just simulation.
Yeah, regardless, this is the best lah. Then later on, yeah, can try to move your attention to another one. I think this is the best right now.
Yeah.
Yeah, so far I think parametric sweep may be the way to go now. You just repeat this for every other parameter, then you find the best spot already.
Yeah.
I think the best spot is the balance spot. Yeah, this is quite a balanced graph. Yeah, I think can just rinse and repeat. Okay, so far, Stephen and Darren, how are you coping? Ken?
Okay, today has a lot.
But do you actually are you able to catch up with the parametric sweep?
Yes.
Just now what they did.
Yes. They're actually trying to make one width as a variable and then check with the parametric sweep, right?
Yeah,
And then you will
correct.
see a different range of when you are using one specific width, what kind of graph it was showing out. So just now I can see there's a lot of different graph from different width.
Yeah, correct.
So
Then
yeah,
you repeat this process for every single MOSFET lah. For example, you have 10 MOSFET in your whole circuit. You simply repeat this 10 times until you find the best point lah.
This is 40 and this is.
Yeah, so which means that you start off with a value whichever you have lah. Then you plot the V out against V in. Then you for every single MOSFET that you want to tune you repeat this process
Because when we did here 40.
Can, right?
Yeah, 40.
yeah, can.
It gave what
Like
we-
just now they tune
It's both at the same.
they tune the top MOSFET until they get the most balanced graph for that value itself. Then they proceed with the second MOSFET. then you proceed lah. You just keep on doing the same thing lah.
Now we're using 40U.
Yeah.
We're using 40U, the range for 40U from 5 to 15 volts.
Can I?
EU.
Yes.
So it's like 38 to 42.
Is
I
okay.
don't know how that will affect.
When will Evan's vacation be over? Ah?
Stability, so yeah, sure.
Yeah, we do this first lah. Then we worry.
You
about-
guys got time to work on it or not?
This is because
We actually have a
for the
result
motor,
for
we
you
have
to
make sure
view.
the stability is
Yeah,
stable.
but I think we're close already. We're close to.
I think if it's stable corner.
You guys try to arrange time to work on it lah. I think at least
if it's just a straight line.
before the sync up session, you
It's just
you need
show
to-
the same results.
at least do what the other team has done so far lah. Can or not?
Yes. So for
Yeah.
the signal station, what we are going to show,
Sorry?
for the signal section tomorrow.
Yeah,
So
yeah.
beside this, what we call the parameter, specific parameter for all the structure in the schematic diagram, and also the graph. I believe tomorrow is actually a suitable time to show them the SC analysis as well, right?
AC ah. Right now, I don't think transient is needed at the moment lah, because we
Yeah.
don't need to analyze anything with respect to time ah. We just see how does the VD change the V out lah.
Okay.
Okay, lah, you go back
Mm.
watch the recording, you do
Yep.
what we did today, and then try to generate the same number of results lah.
Yeah.
Yeah, like you run you show them different curve, which curve you find is the best, and what is the value of the MOSFET that produce this kind of curve. Yeah, do this kind of thing lah.
Mm.
And then also explain lah. We also need to explain, for example, you can say a relationship lah. Let's say just now lah, we change by increasing the width of the MOSFET. What do we increase? We increase the ceiling, or we increase the gradient, something like that lah.
Mm.
Can right?
Can.
Yeah. Tomorrow I won't be there. Tomorrow I will be very busy whole day. So it's up to you guys already.
Mm. It's okay. We can share you the Excel file. So if you have free time, then you just refer to the Excel file what we have done.
Yeah, can.
Yeah. Inside the Excel file, we have put some graph for you to refer to see what's the relationship between the parameters.
Just now.
Yeah, and then
I'm the best
you
one.
make sure everyone actually view the recording lah, and then
Mm.
you all can take turn to run the simulation lah. For example, you can split your job lah. One person handle a few MOSFET lor.
Yes, that's correct.
Right? So you understand how we choose the best value from here, right?
Yeah.
Yeah, okay, then good lah. I think we end the meeting for today.
Yeah.
Okay,
Sure,
I'll
sure.
see you next time. Make sure
Mm.
you guys work together.
Yeah.
Okay, bye-bye.
Thank you, everyone. Thank you totally.
Thank you.
Mm.
Stephen.
Yes.